This is the first of a three-part BocaPhysics introduction to particle physics. In this first lecture, we'll discuss the early history of particle physics, some of the methods that were used to discover some of those particles. In the second lecture, we'll move on to the classification schemes. And then in the third and final section, we'll talk about the eightfold wave, the quark model, the color model, and briefly mention some of the features of the electron theory, and then wrap everything up into the standard model. Now, the field of particle physics can be said to have begun with J.J. Thomson's discovery of the electron. What he noticed was that cathode rays that were produced by from emissions from a hot element were deflected by a magnetic field. So what that told him was that the cathode rays carried some kind of current. So then he had the idea, well, if you could pass those cathode rays through crossed electric and magnetic fields and adjust the strength of the fields, then he was able to measure the velocity and charge per mass ratio. And basically what he found was that there were particles, and he termed those corpuscles, and he called the charge electron. Of course, we call the particles themselves electrons. But anyway, that was Thomson's great contribution. And the mass of the electron is 0.511 megaelectron volts over c squared. Now, in particle physics, it's a lot more convenient to express mass this way than in terms of kilograms. So 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. And C here is just the speed of light. And if you go ahead and do the math here, you'll see that this is actually you'll wind up with the mass expressed in kilograms that you've probably accustomed to using. But anyway, that's mass of the electron. Now, the next particle from the early days, the next discovery is that of the proton. And that was Rutherford's contribution. Thomson had the idea that matter was, could be thought of kind of like a pudding, and that the positive charge was distributed throughout matter. So Rutherford fired alpha particles at a thin gold foil. And what he observed was not consistent with Thomson's model. Basically, he observed that most of the particles passed through the foil undeflected. However, some of them were deflected, and they were deflected at wild angles. So what that told him is that the positive charge wasn't distributed throughout, but rather that it was concentrated in small cores or in nuclei. So Rutherford discovered the proton, and in fact, that's the name that he gave to the positive core of the hydrogen atom. So that's the proton, and we know its mass to be equal to 938.3 megaelectron volts over c squared. Now, the third member of this triumvirate is the neutron. And that, of course, electrons carry negative charge, protons carry positive charge, and neutrons carry no net charge. And those are harder to detect, and they interact usually only with other with nuclei. So have this kind of a reaction taking place. You get a neutron and reacting with boron and then producing lithium in an alpha particle. The alpha particle carries charge, so that is very easy to detect. So that is essentially how the neutron was discovered, and that has mass 939.6 megaelectron volts over c squared. Okay, so those are your electron, your proton, and your neutron. Now, electrons and protons are stable. That means they don't decay away. Neutron, however, outside of the nucleus is not stable. It has a lifetime roughly at about 880 seconds. So long enough to do experiments without a huge amount of trouble, but certainly not compared with modern day particle physics. But anyway, that's the electron, proton, and neutron. The last particle I'm going to tag on, no, it's not part of this triumvirate, is the photon. Now, Planck had the idea that electromagnetic energy, radiation rather, is quantized. So energy is equal to this h, Planck's constant, times the frequency. And Planck's constant has value 4.14 times 10 to the minus 15th electron volt seconds. And again, nu is frequency. So Einstein took Planck's idea and he carried it very much further. In fact, incorporated it into his explanation of the photoelectric effect. So I don't want to get into that because that actually is going off into a whole other lecture. But anyway, photons don't carry charge and they don't carry mass either. So we got our electron, proton, neutron, and photon. So those were the really early days. Now there were three big discoveries that occurred that really set the stage for what we now know as particle physics. At this time, with just these particles, you really couldn't say that you had a field. But there were three big things, and that was Dirac's equation, neutrinos, and Yukawa's theory. So we'll begin with Dirac's equation. Back in the mid-1920s, quantum mechanics was hashed out, the framework was built up very quickly. And probably seen this written somewhere. This is Schrodinger's equation. And basically what Dirac did was make Schrodinger's equation consistent with relativity. In doing that, what we discovered is that electrons have spin, and magnetic moment. Okay? So far so good. But there was one huge problem. Big problem. His equations, Dirac's equation, not only predicted this characteristic of electrons, it also predicted that there were particles with negative energy. So So how to explain that away? Well, these particles, they said, okay, well, they're going to have the opposite charge of electrons, so maybe they're protons. But in Dirac's equation, those particles that have negative energy have to have the same mass as the electron. So they're obviously not protons. What he discovered was that those particles had the same mass, same magnitude of spin, and magnetic moment. But opposite charge. So in fact, these are whole new particles. Certainly would have made life simpler if those unknown particles were just protons, but of course then life would be far, far less interesting. So these actually are what we now call positrons, and they are the antiparticle counterparts of electrons, okay? So at the stage that he made his prediction, or rather his equation predicted the existence of these positrons, there was as yet no experimental evidence for that. Now, a few years later, the American physicist Carl Anderson was looking at cosmic ray tracks in a cloud chamber. And the interesting thing about cosmic rays is that they can carry energy that is larger than anything that can be produced in even the most powerful accelerators today. So they certainly have the energy to produce whatever particles Dirac predicted. And his theory predicted that you need at least enough energy of 2 times the mass of the electrons times c squared in order to make this reaction occur. But anyway, Anderson was looking at the cloud chamber tracks, and what he observed were tracks that looked like this. They were arcs of circles. And what he noticed was that these circles appear to have the same radius. The tracks appear identical. And remember, you have charged particles travel in a circular path if they are in the presence of a perpendicular magnetic field. So the radius of the trajectory is equal to mass times velocity over the magnitude of the charge times the magnitude of the magnetic field. So you can measure the radius of these tracks, and also you know what magnetic field is imposed upon this cloud chamber. So you can figure out, well, gee, these 2 particles have the same mass, they have the same charge. However, they have to have opposite signs. Why? Because they're going in different directions. One's going in a clockwise direction, and the other one's going in a counterclockwise direction. So that was Anderson's big contribution, was the actual observation of the production of an electron and positron pair. Now notice that I didn't draw any tracks leading up to that, and why is that? Well, you had a cosmic ray coming in, and it collided with something, collided with the nucleus. And it created our, electron and positron pair. Should have a plus up there. Okay? So that's the reaction that we'll talk about next. Why does it have to collide with anything? Why can't you just have a cosmic ray photon just decay away. Is that reaction or decay possible? And the answer is a resounding no. So think about this. We've been talking about these reactions in Dirac's Schrödinger's equation and Dirac's equation, but underlying everything, there are certain things that must be conserved. Charge has to be conserved. Well, that's certainly the case here, okay? But energy and momentum must also be conserved. Turns out, not only is charge conserved here, but energy and momentum. However, in this decay, you can't have conservation of energy and momentum both be satisfied. So this reaction doesn't occur, and I'll show that right now. So let me erase some of this stuff on the board. Prove that that decay does not occur, I'm going to assume that it does. The argument proceeds as reductio ad absurdum. What we're going to find is that if we make that assumption, they're going to wind up with inconsistent results. Ergo, that reaction or decay does not occur. So we assume that it does occur, though. We have a photon decaying away into an electron, and that's written as e to the minus plus a positron, which is e to the plus. We have our photon streaking in here, and it just spontaneously decays into two particles. So what I do know is that both conservation of momentum and conservation of energy must hold. And find it convenient to, and here I don't want to goof up, get anybody confused with the notation, but gamma is used to indicate a photon, but it also is used, if you've taken relativity, to be equal to 1 over 1 minus beta squared, and beta is equal to the ratio of the velocity of something with respect to the speed of light. So don't confuse this one with our photon. So I'm going to put a little subscript down there, photon. Make sure there's no confusion there. Okay, so what does conservation of momentum look like? Well, momentum, of course, is a vector. So we want to resolve this into the x and y components and orient this such that y is up, positive y is up, and positive x is to the right. Now, what is the momentum of a photon equal to? Well, its energy of a photon is equal to Planck's constant times the frequency, and for the momentum is just equal to E over C. So therefore, the momentum of the photon is equal to h nu over c. Now, on the right-hand side, we've got the contributions from particle 1 and particle 2. So this is going to be mass times gamma 1 times beta 1 times c times cosine beta 1. Okay? So again, because of relativity, we have to include this factor of gamma in our calculation. So basically, remember, momentum is just equal to mass times velocity, and basically resolving that into the x component. So that's mass times gamma 1 times beta 1 times the speed of light, c cosine beta 1, plus mass gamma 2 beta 2 c cosine beta 2. Now, in the y direction, well, our photon is just traveling to the right, so y direction is going to be 0. We'll have mass times gamma 1 times beta 1 times c times sine theta 1. And now the y component is going to be minus mass times gamma 2 beta 2 c sine theta 2. So that is conservation of momentum expressed here. And then we also have conservation of energy. Energy of the particle, photons just equal to Planck's constant times the frequency. And then we have the contributions from the two particles on the right, so that's going to be mass times gamma 1 times c squared plus mass times gamma 2 times c squared. So I'm going to do a little bit of rewriting here. I'm actually going to divide both sides by c. So it's going to get rid of that c and that one. And it'll give me a c squared on the left-hand side. And if I do that in my y component equation, dividing both sides with c, well, that just gets rid of the factor of c. And thirdly, what I'm going to do is I'm going to take conservation of energy expression. I'm going to divide both sides by c squared. Now, if I square this, conservation of energy will wind up with square of h nu over c squared is equal to m squared plus gamma 1 squared plus gamma 2 squared plus 2 times gamma 1, gamma 2. And remember, gamma is equal to 1 over square root of 1 minus beta squared. And beta, of course, is just a ratio of the velocity of the particle to the speed of light. Okay, so now I need to handle this part. Square that first equation, the x component equation. And I'm going to square the y component equation as well. So again, I started with conservation of momentum, and conservation of energy is divided through by c or c squared, and then I squared each of these equations. That's from conservation of energy. This is from the x component of conservation of momentum, and this is from the y component of conservation of momentum. So what I'm going to do next is to add these two equations together. So on the left-hand side, I'll have h nu over c squared, all squared. And then on the right-hand side, everybody has, or every term has a factor of m squared in common. But if I add up this gamma 1, beta 1, gamma 1 squared, beta 1 squared, cosine squared, beta 1, plus gamma 1 squared, beta 1 squared, plus sine squared, beta 1, using that trigonometric identity that cosine squared theta plus sine squared theta is equal to 1, well, that enables me to simplify this to gamma 1 squared, beta 1 squared, and can eliminate cosines and thetas in that case. And I can do the same thing for the second terms in each of these. So that's going to give me plus gamma 2 squared, beta 2 squared, and then last but not least, okay, and of course I can replace this by cosine theta 1 plus theta 2, but I'm not going to bother because basically I've gotten to the point where I've proven the inconsistency. Because both of these equations are equal to h nu over c squared, assuming that this process does occur, the right-hand sides must be equal as well. And if I compare them, what I'll see is that there's no way the right-hand sides can be equal because for a particle traveling at finite velocity, beta is less than 1. Okay? So if I look at compare the terms, there's no way this can be satisfied. So these equations are inconsistent, therefore my initial assumption that this process takes place was not true. In fact, does not occur. Okay? So in order for, if you have electron-positron pair production, you can't just have a photon decay into it. A photon has to collide with something else, okay? Because otherwise, both momentum and energy conservation cannot be satisfied. Okay, so let me just leave it up on the board for a minute before we move on. Okay. Presence of this additional quantity, this collision, then conservation of energy and momentum will be satisfied. Now, what about the reverse processes? What about if you have pair annihilation? So you have an electron and positron, they annihilate each other. Can they produce a photon? And it turns out, no. There has to be at least 2 photons produced. Sometimes more, so maybe we should just write this as photons. But this process also doesn't occur for the same reason, because conservation, momentum, and energy cannot be satisfied for this particular process. Okay? So let's take a look at, let's suppose you do have an electron and positron annihilate each other, and they do produce 2 photons. So what are they going to be? What are the energies going to be? We're going to assume here that these the electron-positron pair have negligible kinetic energy. So basically that means their kinetic energy would be much, much less than the rest masses. So these 2 particles collide or annihilate each other. And in the process, 2 photons are created. And by conservation of energy, what you see is that they actually will each have energy 0.511 mega electron volts. Now it's possible to determine what the frequency of each of those is going to be by using Planck's formula. And therefore the frequency is going to be equal to 0.511 mega electron volts over 4.14 times 10 to the minus 14th electron volts seconds. And we wind up with an answer of 1.2 times 10 to the 20th hertz. Now let's suppose they don't have negligible kinetic energy. Let's suppose that each of the electron and positron have kinetic energies 2 mega electron volts. In that case, the total amount of energy available in this annihilation will be 2.511 plus 2.511 mega electron volts, and therefore each photon after the annihilation is also going to have energy 2.51111 mega electron volts. And you figure out what the frequency of each of those photons is going to be as well. Okay. Now it's the case that not only do electrons have antiparticle counterparts, the positron, but every particle has an antiparticle counterpart. And antiprotons were first created and observed in a laboratory back in the 1950s. So they smashed protons into other protons, and they had these 2 protons plus the production of a proton and antiproton pair. And by the way, notice how I distinguish the antiproton from the proton. I use an over bar, and remember with the electrons and positrons I use as minus and plus superscripts. That's just convention. Okay, and a few years after that, neutron and antineutron pairs were also produced. So protons and neutron, antiproton, antineutron, have the same masses as their proton and neutron counterparts. So the antiproton has mass 938.3 mega electron volts over c squared, and for the antineutron it's be 939.6 mega electron volts over c squared. So it's easy to see what the characteristics, or at least some of the characteristics of the antiproton would be. It has to have the opposite charge. So antiproton is in fact negatively charged, and you can see that charge is in fact going to be conserved in that process, and charge is also clearly conserved here. Now there's might be a question. Neutrons don't carry net charge, so what would distinguish the antineutron from the neutron? Is it the same thing? The answer is no. There are other, there are in fact quantum quantities that are other quantum numbers that distinguish the antineutron from the neutron, and we'll get to some of that in upcoming lectures. But anyway, those were the early days of antimatter production. Now fast forward around 2000, early 2000s at CERN Laboratory, for the first time, researchers there produced antihydrogen in substantial quantities. And antihydrogen is composed of an antiproton and a positron. The remarkable thing is that that atom is in fact stable, and I believe it was in 2010 they published results right around that time period showing that they can find an antihydrogen atom for something like 1,000 seconds. It's a remarkable thing. I do find that their antimatter research that's starting to really be fascinating, particularly with the antihydrogen. And the reason is because, well, because of possible applications, number one. But also one of the big questions is why does matter dominate in our universe over antimatter? Antimatter is just as stable, apparently, as its antimatter counterparts. Antineutron, of course, is not going to be stable. Neutron isn't stable. Remember, neutrons have a lifetime roughly of 880 seconds. The antineutron presumably has a lifetime about the same. So that's a big mystery. If their particle and antiparticle, there's symmetry between them, how does one dominate over the other? Anyway, one of their studies has been to look at antihydrogen and look at charge over mass, and to see if there's any kind of a discrepancy, any kind of asymmetry there that might explain the preponderance of matter over antimatter. And they've also looked at the spectral lines of antihydrogen, and apparently they're the same as spectral lines of hydrogen. All their experiments are basically, they show symmetry up to the level of experimental error. So if any experimental errors or any discrepancies were smaller than the error inherent in the experiment. So far no answer, but anyway, very interesting research. So that is the positron and also antiparticles. Let's next move on to neutrinos. This is a nuclear process called beta decay. And basically what beta decay is that you have a heavier nuclei. Let's say you've got a tritium, and writing it as hydrogen 3-1. It's because usually when you write out tritium, it's capital letter T, but I'm going to write this out because it makes explicit the content of the nucleus. And that will decay into helium plus an electron, or maybe I'll just write plus ... for now. And likewise, copper also decays. Copper 64 decays into zinc plus some product. Basic process is that you have a heavier nucleus decaying into a lighter one plus an electron. Okay? Now, by making use of conservation of energy and conservation of momentum as well, what you'll see is that the energy of the electron is equal to ma squared minus mb squared plus me squared, all over 2ma c squared. I'm not going to derive this expression. For our purposes, the important thing to note is that the energy of the electron only depends on the masses of the particles that were involved. The initial nucleus and its decay products. So you've got B, the lighter nucleus, and an electron. So experimentally, people looked at the energies of the electron, and they should be the same thing. However, the problem was they weren't. would seem to be a huge problem. I mean, if the masses of the components of this process are the same, the energies of the energy of the electron should be the same, but yet they observe different values. So some people say, well, gee, maybe conservation of energy doesn't hold in this process, in beta decay. Wolfgang Pauli, had a different idea. What he said was, gee, maybe it's not just an electron, maybe there's another particle that doesn't have charge. And why would he have said that? Well, if you look at the tracks of this reaction, this particle, whatever it is, doesn't leave anything behind. So it can't carry charge. Number two, it also has to be very light. And Fermi christened this particle the neutrino. And even after this proposal or suggested new particle, a lot of people thought, well, does this particle really exist, or is it some kind of a bookkeeping trick to preserve or save conservation of energy in this process? And put a little bit more harshly, as it's a figment of somebody's imagination. Well, back in the 1950s, happily, a couple of American physicists, and I don't recall the names exactly, but it was Rines and Cohen, did devise an experiment to measure or show the existence of the neutrino. Essentially, their apparatus consisted of a very large tank of water placed by a nuclear reactor. And in their experiment, they had all these possible, all these neutrinos obviously being generated by those processes. And they only expected to find 2 or 3 interactions or observable interactions an hour. And in fact, they did, and said, okay, well, there is such a thing as a neutrino. But it is a troublesome particle. It's even troublesome to this day. And by the way, we now call this, turn this to be an anti-neutrino. I just said that every particle has an anti-particle counterpart. So neutrinos, based on current understanding, do have anti-neutrino counterparts. And there are some troublemaking physicists, however, though, who have said, no, maybe not so fast. Maybe the neutrino and anti-neutrino are distinct particles. Maybe it's the same thing. So they've proposed experiments for looking for these extremely rare interactions that would basically show that the neutrino and the anti-neutrino is the same. Point here is, I'm not trying to be snarky. What I want to drive home is that particle physics is an ever-evolving field. And for anything in physics, you have to be willing to look at the experimental evidence. And if your models don't describe the physics, don't describe nature accurately, if there's a better way to describe it, then you've got to move on. That's the nature of this field. So we are going to assume in this lecture, because it's based on what everybody knows now, what the current level of understanding is, that there is such a particle as the anti-neutrino, which is distinct from the neutrino. Okay? So anyway, that is the neutrino, first proposed because of beta decay, and then also finally experimentally observed back in the 1950s, and still the subject of controversy even to this day. Oh, and one more point. Originally, neutrinos were thought to be massless, but now it is believed that they carry very small mass. That is an area that continues to be researched actively. So that is, we've covered 2 of the big fields. Now let's go to the third big discovery, and that is Yukawa's theory. flash back to the 1930s. We're bouncing around the decades of the 20th century. And anyway, people understood the photon to be the mediator particle of the electromagnetic force. So what I mean by mediator is basically a particle that carries force, a force carrier, if you will. So the photon serves as a mediator for the electromagnetic interaction. Yukawa's idea was that maybe there's a mediator particle that carries the strong force. And I should say that the strong force actually was proposed because if you think about nuclei, with the exception of hydrogen, they're composed of more than one proton. Well, you know, because from electromagnetism, that light particles repel and light particles attract. Well, if you get a bunch of protons in your nucleus, there should be a tendency for them to repel each other. Yet they don't. The nucleus stays intact. So that was the reasoning behind proposing the strong force. And Yukawa said, well, maybe if there's a mediator for the electromagnetic force, there's a mediator for the strong force as well. And he estimated the size of this mediating particle. So the size of nucleus is on the order of 1.5 femtometers. That's garnered from basically a bunch of data. And we'll say it's about 1.5. Okay. Now this particle has to exist, assuming that information travels at the speed of light, that this has to exist for a time of R naught over C. Or 5 times 10 minus 24th seconds. So that's the lifetime of mediator. We also know that the uncertainty principle must apply. So delta E times delta T is greater than or equal to H bar. Or if I know what the lifetime is, the order of the lifetime, I can figure out what roughly what kind of energy are involved here. And if I know the energies, well, I can write this in terms of the mass. That tells me the mass of the mediating particle is on the order of 130 megaelectron volts over c squared. So I want to emphasize this is absolutely not a rigorous calculation. If you look in different textbooks, different authors can come up with slightly different numbers here, but the point of it is they all have about the order of magnitude on the order of 100 megaelectron volts over c squared. And by the way, if you try to apply this analysis to applying it to a photon, for instance, you'll wind up with nonsense results. So just bear in mind the limited use of this, okay? It's not rigorous, but it is a useful guide. So people wanted to search for this mediating particle, like mediated between the nuclear force binding those nucleons together. And seem to have found it with the discovery of the muon. Muons have a mass of 105.7 mega electron volts over c squared. The problem, though, is that muons don't have strong interactions. So therefore, this was not Yukawa's particle. And actually, he termed it a meson. So when we get into classification of particles, see, muon is definitely not a meson particle. But again, that's for an upcoming lecture. So this was Yukawa was a meson. However, Pion was discovered. In fact, there are several members of the family. Well, actually, for muons, there's a muon and an anti-muon. Pions, there's a pion, anti-pion, and there's also pion with no net charge either. These two have a mass of 139.6 mega electron volts over c squared, and pi 0 has a mass of 135 mega electron volts over c squared. And in fact, the numbers that I came up with is really deceptively close. We're really just looking for an order of magnitude, and as I said, different authors come up with different numbers. Anyway, the pion was, in fact, the particle predicted by Yukawa. Nowadays, of course, we have a different picture. Basically, we know that a lot of particles, neutrons, protons, pions, are actually composed of a smaller number of particles, or rather composed of smaller particles, which are termed quarks. And the strong interaction between those quarks is mediated, in fact, by gluons. But again, that's for another day. Muons, however, are fundamental particles, are not composed, anyway, as far as anyone knows, of smaller particles. Okay, so that is Yukawa's theory and Yukawa's meson. His big contribution was in proposing that there's a mediator particle for the strong force, and also he predicted a particle has a mass roughly in the order of 130 mega electron volts over c squared. I'm going to close this out lastly with saying that the pion and the muon are not stable particles. In fact, they decay. The pion decays into a muon plus a neutrino. And I will be explaining that terminology in greater detail in the next lecture. And the muon decays into an electron plus an anti-electron plus a muon neutrino. Again, I believe it's back in the 1950s. This track was first published, or a track that looks like this. When you have a pion, you can see where the decay occurs. There's a sharp corner here. It decays into a muon plus the anti-neutrino, and then the muon lives for a certain length of time, and then it too decays, and it decays into an electron and also two neutrinos, so actually a neutrino and an anti-neutrino. An electron, of course, is stable. And finally, instead of relying on cosmic rays, people have built accelerators to investigate these interactions. So we'll close this lecture out with looking at the three kinds of particle accelerators: the linear accelerator, the cyclotron, and the synchrotron. This linear accelerator is composed of drift tubes of differing lengths. Each drift tube is hooked up to an AC power supply. The drift tube is so called because inside a charged particle experiences no electric field. Once the particle reaches the gap, it experiences an electric field due to the potential difference between that drift tube and the next one. The particle is thereby accelerated until it reaches the next drift tube. The lengths of the drift tubes are chosen such that the potential between the tubes is a maximum as the particle reaches the gap. In present-day line X, the charged particles ride an electromagnetic wave. Ernest Lawrence came up with the idea of causing the particle to cross the same potential difference over and over again. This is the basis of the cyclotron. The cyclotron is composed of a large magnet that produces a uniform magnetic field. The green arrows indicate the presence of the magnetic field. And also there are a couple of hollow electrodes called Ds because they are D-shaped. And the Ds are hooked up to an AC supply. Particles are injected near the center of the cyclotron and are turned in a circular path by the presence of the magnetic field. The particles accelerate each time they cross the gap between the Ds, so they gain energy and the radius increases. One problem with cyclotrons is that as the particle's motion becomes relativistic, the particle gets out of phase with respect to the AC supply, so the frequency of the supply must be decreased. This is the basis of the synchrocyclotron. There is a practical limitation on the sizes of the cyclotrons because it would require larger and larger magnets to keep providing a uniform magnetic field. So now we next turn our attention to the synchrotron. The synchrotron causes the particles to travel with constant radius. There are magnets around the synchrotron that cause the particle to move in a circular path, and then there are electrodes as well that give the particle a boost. Particles are injected, and once they acquire enough energy, are ejected.